Okay, so it's a pleasure to have here for the last seminar, official one, of the season, Professor Haardt, and then I stopped with the titles, and Francesco. I think we know each other since many years. Too many. No. Despite he looks much older than me, he's actually younger, but okay, stop joking. Francesco is a full professor at the University of Insubria, and he did many things in his career, and is famous for the thermal componentization models for active galactic nuclei. There are 2 seminal papers with a number of citations, and I'm sure that the students are aware of the leading model for the emission for the X-ray emission in AGN, and he did also some relevant work on the intergalactic medium and UV background with Piero Madao and others, and among other things. Now we moved to a slightly different topic, and today we talk about strange new worlds, effects of X-ray, high energy radiation on exoplanets. Not only X-ray. Not only X-ray.
UV and
Thank you very much, Francesco. Okay. The floor is yours.
Thank you very much. First of all, let me thank the organizers for the kind invitation. It's always a pleasure to be in Bologna, and I have a special link to the city. Half of my blood is from Bologna, so it's my mother was from here, so it's a good thing to be here. Okay, today I would like to talk about the work we have been doing in common in the last, I would say, 4 years on exoplanets. We started a small team a few years ago working on that. I found myself interested in exoplanets science. I was reading archive papers on exoplanets, so at a given point I said, let's do some research. Since I know something about the physics of the intergalactic medium, what is the thing that I could do with minimum effort? And it was something related to the effect of high energy radiation on the atmospheres of exoplanets. And we started that. And of course, I have to say that most of the work, as usual at my age, has been done by PhD students. Okay, especially Andrea Caldiroli, now PhD students. It was a master students in Como. Now it's in Vienna as a PhD student. Federico Biassoni is PhD students in Como, and Riccardo Spinelli was a PhD students in Como. Now it's a postdoc in Palermo. He's working in a group of the Giudice. And then there is another faculty, Elena Gallo, and the University of Michigan. Then other people, and you may know some names here, especially Giovanni Ghisellini, and these 2 last guy, Maschi and Rocha, are in the University of Michigan. And they helped us with this. Let me see. Okay. Nothing happened. Good. Nothing happened. This is good.
Click on the presentation.
Okay. So I have to do this, okay, on the pad. Okay, so let's see why we are interested in that. We say, okay, just a brief introduction. The pace of exoplanet discovery has been increasing in the last 10 years, thanks to Kepler mainly. And today we know more than 5,000 exoplanets, and there are 1,000 more that are await confirmation since we are not seeing the exoplanets. We are seeing the stars. This is it. And we now believe, in a sense, that every star in our galaxy has at least 1 planet, most probably more than 1. So there is a lot of exoplanets in the galaxy. And there is a fraction of these exoplanets that orbit the star in the so-called habitable zone, which is a very loose concept, let's say, where the conditions are such that the water can exist in the liquid form. Because we think, well, we believe, since we have a statistic of 1 related to the formation of life, that water is an essential, fundamental ingredient for the formation of life. So we call this as the habitable zone. And of course, first order, the habitable zone depends on the luminosity of the whole star. It's clear that some stars have intense extreme UV. For EUV, I'm talking about ionizing radiation, so with energies larger than 30.6 eV. okay, or one Rydberg, and also X-ray that can cause heating and evaporation, for example, of the water from the planet's surface. Okay, this is called desiccation. So it could be very harmful. And on the other hand, there are indications that a planet to become life-friendly has to lose his own primordial hydrogen helium envelope. Okay, so the effects of EUV and X-rays are bimodal in a sense. Okay, they could remove the primordial envelope. Primordial, I mean hydrogen and helium, like it's the atmosphere of planets like Jupiter and Saturn. While on the other hand, if you have too much UV and X-ray, they could make water evaporate. And this is something you don't want to do that if you want life on the planet. And so, in the end, full characterization of the role of radiation is a necessary ingredient if you want to, in the end, to identify the targets that are suitable for the so-called life as we know it. People usually say life as we know it. There could be other forms of life that we don't know. Also, radiation can play a role in determining the observed distribution of the radii of exoplanets. What we have done is to attack some of these problems from using different wavebands in the electromagnetic spectrum. We start talking about EUV, ionizing radiation, okay? And it's clear that if we have the so-called super Earth, I will show you in a while what a super Earth is, and gas giants are Jupiter and Saturn, these kind of planets, the ionizing radiation could cause very large mass loss from these planets, okay? The other thing is that if we move down to a longer wavelength, near UV, talking about 200, 280 nanometers, okay? In this case, this very radiation, there are indications that can be very harmful for life forms. It could destroy the DNA, okay? We have the ozone layer, but UV radiation, direct UV radiation can be very harmful for life forms. On the other hand, there are laboratory experiments that say that NUV can help to synthesize RNA, which is a fundamental ingredient for the formation of life. Again, here, the effect of UV is bimodal. And the last thing that we have studied is the effect of galactic transit, like gamma ray bursts and supernovae that can explode close to planetary system, and the gamma rays can destroy the ozone layer. So in this case, the UV radiation, if we don't have the ozone layer, the UV radiation from the sun, from the host star, can really damage all the life forms on the planet itself and cause mass extinctions. Okay. Also, there are indications again that this kind of situation where we have an intense gamma ray illumination of a planetary atmosphere can trigger global cooling. That maybe is not a bad thing, but okay. So the talk outline is the following. We start to see the effect of XUV. Okay. There are a set of papers that we published in the last years. Then we move to stellar NUV. Those comes from the host star. And in the end, we show you something related to the effect of galactic transits on the habitability of exoplanets. Okay, let's get started. Okay, XUV. Okay, UV X-ray photons can ionize, of course, hydrogen and helium. The photoelectrons hit the gas, and the idea that the energy of the photoelectrons goes, a fraction of the energy goes into expansion work, PDV work. And so we have the expansion of the atmosphere because we are dumping energy into the atmosphere. However, there are competing effects, basically radiative cooling. It's not clear what is the fraction of radiation, which is transformed into expansion work, compared to the fraction of radiation, which is instead radiated away as cooling lines, especially Lyman alpha and other things like that. And there are a lot of work starting from mid-2000, and here there is an incomplete set of references on this subject. Do we see Do we observe outflow in atmosphere? There are indications that we actually observe some outflow in atmospheres from exoplanets in Lyman alpha. Okay, there are a bunch of papers where there are indications of the emission of this outflowing gas. However, Lyman alpha is a bad probe from outflowing gas for two reasons. The core is severely absorbed by the ISM along the line of sight, so we just can observe the lines, the wing of the line, which have a very large velocity compared to the systemic. Let's say about 100 km per second, which is much larger than the velocity of the outflow that you expect. So probably what we are observing here is something not related to the outflow that we are observing, 100 km per second, are not driven by radiation. Probably they are more connected to stellar winds. And also the other thing, of course, is that Lyman alpha is all observed from space, so it's not an easy task. Another possible probe for outflow in atmosphere is a line from neutral helium. It's a metastable state of neutral helium, which has a transition here. You see about 10,000 Angstrom, which is good. It's not absorbed by the ISM heavily, and also it can be observed from the ground. So it's much easier to do this. I will return on this later on. Okay. Do we see photoevaporation again? Yes. This is. I just want to show you this plot. The planet side. Those are the super Earth. This is in units of the Earth radii. So super Earths are from 1 Earth radii to, let's say, 1.7. And then we have the sub-Neptune. This is the frequency of planets that we observe per star. Okay. And apparently there is a bimodal distribution. Okay. This is called the Fulton gap. The fact that we are missing some planets in this region where the radius is about 1.8 Earth radii. And there are indications, there are theoretical work, especially by Owen and collaborators, that say that this could be caused by photoevaporation. Okay? And it depends if the planet has a massive core, okay, or if the core is not as massive. If it's not as massive, the atmosphere can escape. If the rocky core is massive, the gravity is larger, and so it's harder to make everything evaporate. So we got the so-called evaporation part. Okay, energy limited photoevaporation. Okay, the simplest way in which we can study how the atmosphere of an exoplanet expands because of irradiation is the so-called energy limited approximation. It's an argument that traces back to Watson in 1951, and in the end, it's simply energy conservation, nothing more than that. I show you here a very simple equation. Here, you may recognize that this is the this is due to gravity. Okay, m is the mass of the planet, m dot is an accretion rate or the mass of the state, depends on what you like. And here we got the flux of XUV radiation, and this is the cross section of the planet. Okay, the first thing to note is that this guy here is, if you make a simple argument of units, is PdV work. Right? This is PdV work, nothing more than that. And it's nice to see that this is just like accretion. In accretion, you have an increase of m dot accretion, and you release radiation. In accretion, this, for example. Here you have an accretion of radiation, and you release mass. But it's the same thing, exactly the same thing. Okay. There are, of course, ignorance in our arguments here, because we don't know how much the fraction of radiation which is actually transformed into expansion work, as I say, and also we don't know where is, okay, we don't know the XUV radius of the planet, because what we know is the optical radius. When the planet transits in front of the star, it gives the size of the planet, but we don't know the extension of the atmosphere. Okay, and so we don't know that. As usual in astronomy, what we do is to recast all our ignorance into a parameter that, as usual, has a value around 10%, which is the standard value that you assume that you put to any parameter that you don't know. Okay?
Usually call it eta.
Eta. Exactly. Eta is for efficiency. Okay, whatever. 10% is it. There are, I counted about 20 parameters that star formation rate, efficiency of black hole accretion, and 0.1. Everything is 0.1.
Viscosity.
Viscosity of disk, alpha disk, but it has a psychological motivation for that. If you say it's 1, you say, but if I'm wrong, if you say 10 to the minus 3, say who cares? So 10% you could say. No, that's true. Okay, so and so in this way you can recast this is gram per second. Oh, this is okay. This whatever. Okay, those are gram per second. The mass rate as a function of the flux of the illuminating flux. Here there is the density of the planets. Simply write the m divided by r cubed as the density, and there is k is an extra parameter that modifies the potential of the planet because there is the star that is pulling effect. Okay. The question is the efficiency, this eta, a constant or is a function of mass and or the XUV flux? In literature, a lot of people assume that this is a constant value, 0.1, for example, 0.3, 0.5, whatever. What we have done is just to try to see in a more detailed way if this eta depends on gravity and on the irradiation. And to do that, very simply, we build up a very simple 1D hydrocode solving the Euler equations. Okay, I don't want to enter into any detail. This code is publicly available, and this is something that I discovered in the community of exoplanets. It's very rare that people release their own code. I found this very strange, but this is it. And in fact, when we first submit the paper, the editors say, "Oh, we are very happy because you are releasing the code." Okay, whatever. And this is 1D code, very simple. It's very fast compared to other 3D code, of course. And there are, of course, energy balance, heating, cooling, and ionization balance. And the thing is set. We select, okay, we've done the code. We select a sample of 21 planetary systems with observed X-ray emission. Why we need observed X-ray emission? This is a crucial point because we do not observe extreme ultraviolet radiation. The radiation that is making all the job, okay, ultraviolet, is not observed. Just a bunch of stars have been observed, close by stars, okay? And otherwise, we have to relate X-ray to EUV through scaling relation, which you can imagine are not carved in stone, okay? They have a lot of uncertainties. 2 orders of magnitude at least, okay? And I will show you later on. Okay, we selected these planets here, and we basically from Gaia distances, and we got the X-ray luminosity. Then we applied these uncertain X-ray UV relations, okay, and then we got EUV luminosities. Then we could find all the parameters. I don't enter into any detail of the planets, going from stellar density, stellar radius, stellar mass, planet radius, and planet mass. You can do that if you have both. We said the planets where there are both the transit and radial velocity information. You need both of them if you want to find all the parameters of your star planet system. And we have done that. Okay, no, this is it. Okay, so the thing is, okay, let's do some simulation with our code. And this m dot is what we sort out from our code, and we recast into this effective efficiency. Okay, this comes from simulations, and we say, okay, this gives you basically the fraction of the injected radiation, which is converted into expansion work. And those are the results. Okay. In these plots, we have here the efficiency that we found, and this is the gravity of the planet with a minus sign, so the absolute value should be negative, so put it positive, okay? And you see here, 1 means 100% of the radiation is transformed into expansion work. And you see that there is a clear divide from the so-called low gravity planets to high gravity planets, and where this efficiency drops by orders of magnitude. And so there is a clear indication that the efficiency depends upon gravity. And there is a dividing line, I would say, about where the logarithm of the gravitational potential in Earth per grams is 13. For planets with a gravity larger than 10 to the 13, or minus 10 to the 13, the efficiency of mass outflow is very, very low. Okay, this was already known. What we found is just to see if we could find a good reason for that.
So the choice of 10% was not that bad.
Not that good. Not that good.
Not that good.
Not that good. The usual people say 10%.
Well, it's much higher in low
yeah,
gravity
yeah,
planet.
but you have other uncertainties. Right?
Okay, it has been
Yeah,
divided.
we found that it's close to 100%. We found that it's close to 100%. And okay, so the idea was.
Francesco, can I ask something?
Yeah, sure.
The uncertainty on the scaling relation to X-ray and UV, which direction would change that? Like the in normalization or?
In normalization. I will show you in a while the effects of radiation on that. Okay. So this is just to say that there is effect on gravity on the efficiency. Then I will show the effect of radiation on efficiency. Okay, so I say, okay, why is 10 to the 13 there is a dividing line? And we found a very simple argument. Okay, you can work out the so-called mean excess energy, okay, that measures the amount of energy that per ionization event is still available to heat the gas. This is a concept that I borrow from my knowledge in the intergalactic medium. This is something that I use when I work on UV background, okay? This mean excess energy, okay? And it's simply the photoheating rate, you see here, divided by the photonization rate, okay? This is an energy, and the nice thing that it's independent upon the flux normalization. It depends only on the shape of the ionizing flux, okay? Because you have F here and F there. It's not depending on the normalization of the flux. Okay, so let's say, okay, assume a pure hydrogen gas, power law, nu to the minus beta, beta of the order of 1, and you work out easily this, sigma goes like nu to the minus 3, or these kind of things, and you find that this energy excess is of the order of 5 eV for a typical spectrum, for a typical energy spectrum with a power law index of 1, minus 1, okay?
So, just, is the energy which is left after you have ionized the atoms, and then the surplus is.
Exactly. Here you see, if you exactly nu T, this is 0, because the photoheating rate. Nu T is a frequency of 30.6 eV. Okay, fine. And they say, okay, now we say, okay, particle of mass m, a proton, can escape if its excess energy exceeds gravity. So if this delta E is larger than phi p m, and you find easy that phi p has to be lower than 10 to the 13 gram per gram. Okay, so there is a reason, a basic reason why we have this dividing line from low gravity planets and high gravity planets. Okay? And it comes from this very simple argument. Here in this plot, this is m dot, okay, times k, doesn't matter. This is F, the flux divided by the density of the planet, so they should be linear, okay? Remember, rho is for all these planets of the order unity. They are weights like water, basically, so it's not a big, you can easily go from this F divided by rho to F. And you see that actually, this is the effect of radiation, actually, this efficiency 100%, 10%, 1%, okay? Those are the light planets, low gravity planets, and it seems that the efficiency is independent upon flux, but only up to, let's say, 10 to the 3 in this unit. Later on, what happens is that the efficiency decreases. You have an efficiency which is independent of flux if it follows one of these straight lines, okay? And this happens, okay, for low gravity planets, the so-called the outflow in so-called energy limited approximation, PDV work drives the outflow, efficiency 100% only in this region here for low gravity planets, but also low irradiation. Okay, why? Because at higher, when the radiation is higher, what happens is that your outflow, the temperature of your outflow, thermostat up 10 to the 4 Kelvin, which is a typical temperature of a photoionized gas. And then you start to build up an efficient relative cooling. So you inject more energy, but the energy is not transformed into expansion work, but in cooling radiation that you lose. And so the efficiency of mass outflow is decreasing. And you see that, this curve here. For high mass planets, those guys here, the efficiency is much lower, orders of magnitude lower, 1%. Those are high gravity planets, above 10 to the 13. And what you see here is that what we found is that radiative cooling is always dominating the activity. The gravity is too large, okay, for these planets. The radiation is not able to make the atmosphere escape. And what you have is that radiative cooling is dominating. Fine. Few things more about this metastable helium-1 transit. This is the line that we want to observe, and it's been observed in few planets. Okay, it's a triplet line. Those are the wavelengths. Okay, it's observed from the ground, and it has been observed in 8 planets with an absorption depth of few percent compared to when the planet's off transit. And it's not observed, but it was expected to be in at least 20 planets, and we will see. Maybe we will understand why. What we have done is just to make an extensive analysis of the process, building a suite of other simulation with different spectral types for stars, different distance of the planets from the stars, to see how the helium-1 signal depends on the planet parameters in terms of stellar emission, distance from the stars, and other things. And also a crucial point also is the abundance of helium that we don't really know. People use 10%, 0.1 compared to hydrogen, but it's not clear if it's really, planets. This is solar abundance. Okay, the helium solar abundance is 10% compared to hydrogen, but we don't know if it's true there. Okay, and just to give you an idea of we tested how many 6 stellar types from M4 red dwarf to G2, which is the sun. Okay, and apart from the sun, which is the purple here, all this emission here is reconstructed from models. Okay, and there are huge uncertainties here, especially from M stars. Okay, because we do not observe this emission from M stars. It's very difficult to observe. Now there is a proposal by Kevin France of a satellite called ESCAPE that should, in principle, enlarge the number of stars with measured EUV radiation. We have to rely on X-ray that we can observe in stars and make some, scaling relation to build this guy. Other relation comes from Lyman alpha emission. From Lyman alpha emission from the star, you can have an estimate of the EUV. But again, Lyman alpha emission from a star it's hard to observe because Lyman alpha is absorbed along the line of sight. Whatever. What we have done, don't worry, those are typical output of our code. These are density as a function of the radius of the planet, of the distance from the surface of the planets, units of the planetary radius. Okay, this is temperature, velocity, a lot of things. The important thing is here, this is the number density of helium-1 in this metastable state. This metastable state has a lifetime of about a couple of hours, so it's a good state to try to see an absorption line. And just to give you an idea, this is the fraction of the helium-1 in this state. It's of the order 10 to the -5 compared to helium-1 in the normal ground state. So it's very, very small, but still observable. And here we have we made a module that radiative transfer thing, and you have the absorption depth that you expect from these arguments. The thing that there is the bottom line strong dependence of the stellar spectrum. Okay, K and M types give the deeper signal. Okay, while a G type star like the sun has a very low signal because there is a huge far UV emission, and the ionization potential of this metastable state of helium is about 4 eV, while on the ground state, helium-1 is ionized. You need photons about 24 eV. It's just 4 eV are enough to ionize the helium, and the sun compared to the other stellar type has a lot of far UV emission. Okay, so the thing is that we computed the theoretical absorption depth that turns out to be much larger than what is observed, much larger. Okay, we expected from our model to see not just us, all the people that work on that done this, there are a bunch of groups, they expected to see absorption from few percent to 10%. Actually, what you observe are less than 1% absorption. And in many systems that where you expect to see helium-1 in absorption, you don't see nothing. So the question is why, okay? Of course, again, helium abundance can play a role here. If you put less helium, we have less absorption signal. And also there are indications that the stellar wind can play a role here, because the stellar wind can really damp the outflow from the planet. If you have a star with a strong stellar wind, okay, the outflow from the planet can be damped, and you don't have an outflow. But this is something that we cannot override. Just to give you an idea, this is we test a different helium to hydrogen number ratio. This is 0.1. Here we have the same number of particles, alpha particle and protons here, okay? And here we have 10 to the minus 2. And for 3 different XUV spectrum. This is a nominal XUV luminosity. This is divided by a factor of 10, and this is multiplied by a factor of 10. And you see that there is a clear degeneracy between how much XUV you have and the helium abundance, okay? And this is the absorption depth that you expect. Let me say that all observations are below 1%. So XUV, helium degeneracy. Okay, summary for this part, which was the longest part of worry. The next two will be much faster. We analyzed 21 stars with 24 closely orbiting exoplanets with XMM and Chandra data. We revised planetary parameters using the Gaia data release 2. We use ATES, our 1D hydrocode, okay? And we make a suite of simulations for all these planets, and those are the results. We found that there is a maximum gravitational potential for efficient energy limited atmospheric escape, which is understood in terms of the mean excess energy, as I showed you. Among the low gravity planets, the mass loss scales linearly with flux only if the flux is below a given threshold, let's say 10 to the 4 per square centimeter. For larger fluxes, we have relative cooling. And the dominant mechanism for losing energy because of radiation is Lyman alpha emission. And for high gravity planets, only a small fraction of the flux can be used to drive outflow because the gravity, yes.
Sorry, just to recap my understanding. Your simulation is for planets with radius between Neptune and Jovian. You made simulation for our
also super Earth.
That means
sub-Neptune. Let's say larger than 2 Earth radii.
Okay, larger than
okay.
just to,
Yeah. We are super Earth, Neptune, and gas giants
okay.
in close orbits, of course. We are talking about the distances from the planets between 0.1 and 0.01 astronomical units.
Yes,
they're
always,
very, very close.
Always to have water in liquid.
Exactly.
Okay. But the dimension of this.
Yeah, exactly. Okay, then M-time star could be prime targets for metastable helium-1 absorption, a combination of 2 factors, because the lower outflow temperature and the smaller stellar radius. Since the star is smaller, when the planet's transit in front of the star is eclipsing a large fraction of the star, and you see a deeper signal. Easy. And the thing that we don't see any, we have not discovered yet any hot Neptune around the dynamic world. So the best plans for helium-1 absorption seem not to exist. And we don't know why that. Okay, the absorption depth is degenerate against UV flux and helium abundance, and again, the stellar winds can play a role in damping the outflows. So this could be some reasons why we do not see strong helium-1 absorption, even though we are expecting to see that. Okay, let's move to near UV abiogenesis. Okay, UV radiation inhibits photosynthesis, causes damage to various species of proteins and lipids. And already Sagan in 1973 said that it may induce DNA destruction and destroys nascent biomolecules. This is bad in red. In green, that any UV radiation, there are recent indication. Those are this guy Rimmer and his group. They are making experiments in lab. Okay. And they basically illuminate this cyanide sulfide with NUV radiation. And after something that I do not understand, I remember it's much harder for me, you know, my permission of chemistry of first year in physics a long time ago. But if you illuminate this composite with NUV radiation, you produce sugars, which are the backbone. Sugars are the backbone of RNA and also DNA. Okay, so NUV radiation is helpful to produce something that you may use to form life forms. Fine, good. And so what we have found is that, okay, suppose that there is, we can measure a minimum NUV level that is able to trigger RNA synthesis, okay? So there is a minimum NUV level. On the other hand, there is a maximum NUV level that life can tolerate. So there is this line, this strip, is what we call the UV habitable zone. It's nothing to do with the liquid water habitable zone. This is the region in distance from the star where the near UV, 200 to 180 nanometers, is enough to synthesize RNA, but not too much to destroy DNA. Okay, good. Okay, here we don't know the atmospheric transmission, so we take three very simple models. F1.0 means that all the NUV from the star is able to reach the surface of the planet. Here only 50% is only 10%. Okay, just we parameterize the absorption of the atmosphere with this simple scale. Okay, fine, but we know that there is the liquid water habitable zone. Okay, this is for hotter stars, it's very far. Sun-like stars is where we are, and this is for cooler stars like M-dwarf. Okay, so the obvious thing to do is to see if there is an overlap between the liquid water, this is called in literature CHZ, circumstellar habitable zone, and the ultraviolet habitable zone that we have just defined. And this is it. Okay, this is the liquid water, let's call it liquid water habitable zone. Okay, as a function of the distance from the planet in astronomical units. Okay, this is the distance of the sun. Okay, we have found there are more than almost 60 planets that are discovered in this in the liquid water habitable zone, and the question is, do they also reside in the ultraviolet habitable zone? And this is what we have found. Okay, which is nice. Okay, this color code here is the effective temperature of the star. So those are M stars, those are G stars and FK stars here. You see here, you recognize at least three stars here. TRAPPIST, okay, that was very famous, that have at least 3 or 4 planets in the habitable zone. But you see that TRAPPIST is very far from the NUV habitable zone. Bad thing. Then what you see, Proxima, okay, Proxima, this is the closest star to us, is in the liquid water habitable zone and only marginally in the UV habitable zone. And then here you recognize this system here. We have Earth and Mars, which are well within the liquid water habitable zone. Venus is marginal. Probably Venus in the past had liquid water on the surface, and they triggered some greenhouse runaway effect and everything.
The fact that you have the Earth there, it's by construction, or it's
No.
not necessary?
No, by construction. It's good. This is the temperature of the sun. It's here, and the radius is 1, and it's in the liquid water habitable zone.
There is liquid water.
There is liquid water. Okay, but again, Mars is in the habitable zone. Yeah.
I mean, thinking about Mars, in fact.
Mars.
Sorry.
No, I was just wondering on the lower limit. So you said that the lower limit can help to form some chemistry. But
Exactly.
There are also other processes that can.
Absolutely, and I'll come in a while. No, in a while. I'll show you why we can use this information. Okay.
Sorry, I guess thinking about Mars, the thing is that all this modeling is telling that you are not you are missing the evolution of the single planet, the history. To our knowledge, we don't know about this?
Exactly. I'll come in a while. The important thing is the evolution of the star.
Okay.
Okay. So the thing is that, okay, planets orbiting the liquid water of M dwarfs are all out of the. This is what we found that we published of the UV habitable zone, which was a bad news in the sense that M dwarfs are 80%, 75% of the stars in the universe, in the galaxy. And the habitable zone around M dwarfs are the prime targets for James Webb, for example, to search for biosignatures. Okay, and so we said, okay, you are wasting your time if you are looking for biosignatures around M dwarfs. Okay, this is not true because you want to look for biosignatures around M dwarf, and if you find one, you may say, okay, this particular pathway to life evolution, which is the NUV radiation to cyanide that produce sugar, is not the correct one.
Or it's not the only one.
It's not the only one, but would be a great improvement in our knowledge and how life is formed on our planet. The thing that we didn't consider, the evolution of the luminosity of M dwarf. M dwarf are very active stars compared to the sun. They have flares and they evolve in time. The luminosity of M stars is evolving in time very, very strongly compared to G-type stars. And this is what we are doing right now. There is a paper by Spinelli et al. Is in progress, work in progress, and we hope to submit this by Christmas, which will not be the case, of course. But this is okay. And this is a paper that's recently was on the archive by Richie Yovel and collaborators. They showed the NUV luminosity of M dwarfs from not so dwarf to very dwarf stars as a function of the age of the star. And you see that there is a clear decrease in the luminosity of the luminosity of the stars in NUV. Okay, NUV from these stars is not from the photosphere, it's not the nuclear burning, it comes from the chromosphere. It's related from magnetic field rotation, things like that. Okay, so it's a difficult, it's not easy to model this from a purely theoretical point of view. Those are observations from the so-called moving groups that I don't know much about it, but they could compute the age. Those are coeval groups of stars that can compute the age and compute the luminosity, the NUV luminosity with the Swift and Galaxy. Okay, and the idea is that we did the simplest thing: take the median value and apply to our planets back in time. And this is what we have done. We took just one planet, for example. This is one star, GJ 273. This is the age that is estimated today in the mega year. So this is 1 gigayear, about the age of the sun. And this is the median value, and this is where GJ is today, and we just evolved back in time with the simplest possible way, following the median evolution, okay? And if you do that, you find this thing. This is the age of the star, okay? This is the distance from the star of the planet. This is GJ 273b, the planet that we are interested in. This is where it is. The green is the liquid water habitable zone that is evolving time because the luminosity of the star is evolving in time. Okay, it was hotter in the past, and so the liquid water was farther out. And you see that at a given point, the planet entered the NUV, also the NUV habitable zone. These three colors are again when you just admit that 10% of the UV is going to the surface of the planet, 50%, 100%. Okay. For this particular case, if 100% UV is transmitted, this planet was inside this overlapped liquid water and UV habitable zone between 95 megayear and 800 megayear after the formation of the star. If this is 50%, the overlap is lower. If only 10%, this planet was never within the habitable zone, the overlap of it. We've done this for all our sample of planets. We looked for some metric to describe this thing, and probably is not the possibly or probably. It's not the most easy thing, but we say, okay, let's compute the time where the two habitable zones, liquid water and UV, overlap by at least 95% of their area. Okay, they are evolving in time. Sometimes they are separated. The evolution of the star makes them, for example, maybe overlap, and then they fall apart again. Compute the time for which these two areas, these two zones, these two habitable zones overlap by 25% in area. And this is what we have found, okay? Those are the M dwarf, okay? This again, 10%, 50%, 100% transmission. And those are the G or K F-type stars, okay? Here, we have a lot of time to develop life, okay? Here, the time is lower. There is an indication that a good candidate could be Proxima. And I would bet a lot of money on Proxima. It's close by, it's not difficult to observe. It falls in the right place, okay? And so Proxima is the place where we could find biosignal, where we should look for biosignators. That's my opinion.
But they did not have a lot of time. I mean,
well, it's 1 giga-year, right?
Okay. No, I was comparing with the G-type.
Yeah, no, sure.
Okay.
Sure. It's between 1 and 2 giga-year.
Well,
Francesco, so it's possible to do the same kind of the size also for the solar system, even if there is not an star.
Yeah,
just to discover when. So
yeah, it was, well, this, I show you this. This yellow line is not the sun, but the mass of these stars is between 0.6 and 0.9 solar masses. And you see there is not much evolution. Okay, those stars are not very much evolving compared to M stars. So if we are in the liquid water and UV overlap, probably we were within the last 5 billion years. Okay, here we are, all set, boom, boom. Okay, this is what we have done. Now I'm almost the last few words on the gamma rays now. Dwarfs are prime target for search of biosignators, but we found that they are out of the NUV habitable zone, but we have to make an improved statistical assessment of what we have done. So far, we have just seen a very simple, we have just used the simplest possible statistics. Take the median value and adopt to every planet. We have tried more sophisticated statistical analysis like the Gaussian processes, but we are not sure that it's the right direction. We are still working on that. Okay, last few words. Gamma rays. We have seen extreme UV, we have seen near UV, and now we go back to very high energy. Transient. We have gamma ray burst. I'm not entering in detail here. Short duration, short gamma ray burst, long gamma ray burst. Different progenitors. These are neutron star merger that collapse of very massive metal stars. And then we have supernovae. Those are transients that emit a lot of high energy radiation in the galaxy. Okay, so the idea is that we asked what are the safest place and time to live in the Milky Way. Okay, so what is the place and time or shelter from high energy events? And this is what we have done. Okay, we took a paper that by Mellot and Thomas that claimed that a typical gamma ray burst at 1 kiloparsec would almost totally destroy the ozone layer of the Earth. Okay, if you don't have ozone, you have the UV can penetrate into the Earth's atmosphere and cause chemical modification, global cooling age. Okay, also penetrating UV radiation can directly alter the DNA. So the idea is not that the gamma rays are harmful. The gamma rays destroy the ozone layer, and then we have the UV from the sun, which are destroying and causing problems to the life on the planet. Okay, we made a very simple thing. Okay, we deem lethal. Okay, and for a planet, an event if it happens within a given distance, which is again say, okay, this is dangerous for life. Okay, the critical distance that we found is such that the ozone layer is severely damaged. And there are indications that you need a fluence that is larger than 100 kilojoules per square meter. This is the fluence of your event, gamma ray burst or supernova. Okay? And we estimated the rate of lethal events occurring along the cosmic history of the Milky Way. To do that, what we have done, okay, this is the Milky Way, okay, a picture that we took from outside, from the Milky Way, and this is where the Earth is, and this is, for example, the area within which you don't want any gamma ray supernova to explode. Otherwise, the life would be in danger, okay? And we have computed this as a function of distance from the Galactic center. I'm not entering any detail. We use a very simple model of Milky Way in terms of stellar density as a function of radius and time, star formation as a function of radius and time, and metallicity as a function of radius and time. Metallicity is important because long gamma ray burst depends strongly on the metallicity. And so the metallicity is evolving in the galaxy, and so we have an evolving rate of, for example, of gamma ray burst, okay? And from the star formation rate, the IMF, we use a simple salpeter IMF. We could estimate the density of terrestrial planets using some scaling relation that link the number of planets to the number of stars. Okay, and so we compute the number of lethal events suffered by planet, and we say, okay, within 500 mega year, half of a giga year, that we say, okay, this is the time that the life needed on the Earth to thrive. And so how many events, lethal events, we have every 500 mega years in the galaxy as a function of time and space. And this is it. In the next plot, which is the last one that I'll show you, the number of lethal events, again, per half of a giga year. And when you see green means the life is safe. When you see red means the life, if there is life, is in danger. And this is our results. Okay, this is the galaxy. This is the radius from the galactic center, okay, from 0 to 20 kiloparsec, and this is the look-back time. We are here now. Red means that we have more than 40 lethal events per half a giga year. Green, less than 1, okay? So this is the galaxy now. This is when the solar system formed 5 giga years ago, and this is at the Milky Way formation. And you see that there are a couple of safe place and time. The first one is an early peripheral green valley in this plot, okay? Star formation was very low, so we had a very low rate of lethal events. On the other hand, the density of planets was very low. This number here is the density of planets per unit surface. It's very, very low. And here we have 2 lines because M type star and FGK type star, doesn't matter, details. And then we have another green valley here, okay, that happened in the last 6 giga years ago, between 2 and 8 kiloparsecs from the galactic center. And we are, you know, not in the safest possible region, but, you know, decently safe from lethal events. In the future, we do not expect to have any danger from transients because the star formation rate is much lower than when it was before. Okay, and the idea that if you see this, the solar system form here, and in the very initial phase, we had a lot of transients, lethal transients, and also some numbers of lethal transients, let's say 1, 2 per half a giga year, let's say 1 giga years ago. And the idea, okay, I'll show you why this is interesting. So this is summary, GRB and supernova potential data for life zone. This is obvious. And there is a maximum fluence that we can use to quantify the lethality of these transients. And we use a very simple model for the Milky Way. And we conclude that most power transients jeopardized by life across most of the Milky Way in the past. Okay, until 6 gigayears ago, the entire galaxy was frequently sterilized by such events. While we find that the two green valleys for life survival, one peripheral, larger than 15 kiloparsec at the early stages, look back time larger than 8 gigayears, and in that particular place and time, the density of habitable planets was probably very, very low. So we do not expect to see aliens from the past. More recently, there is a much closer to the Galactic center. The Milky Way become a safe place. Okay, our results indicates that given the numbers that we found, that we can confirm the hypothesis that a single long gamma ray burst could have been had a leading role in the late Ordovician mass extinction that occurred half a gigayears ago. And what I'm talking about is this. This is the number of genera, thousands, as a function of the age, okay? Look back time. And those are the 5 known mass extinction. This is the dinosaur thing, okay? Dinosaur here. The first, this is the end Ordovician, could be caused by a long gamma ray burst. And we have seen in our calculation, we found that there is a chance that 1 or 2 events of such events occurred in the last 500 mega years ago. So we are all set here. Ongoing and future prospect. In this part, XUV, we are working about planets around white dwarfs. Very weird thing, but there are indications, claim, that there are planets around white dwarfs. That could be a nice thing to do. White dwarf has now they are very cold, but when they are not cold, but they are very, very faint. But when they are formed, they are very powerful. Ionizing emitting radiation, and so it's interesting to study planets around white dwarf. Remember that the first planet was found around the pulsar, so it's would be not strange. We want to study evolution of our model in terms of atmosphere and loss retention. We want to put metal cooling and molecular hydrogen into the code, and there is we are working. Well, let's say working is too much, but we want to build up a three-dimensional code on GPU. Okay, there are many three-dimensional codes that works on CPU, but on GPU there are no public code on that, and we would like to do that. Stellar UV, we want a more evolved statistical analysis of what of the assessment of abiogenesis and dwarf, and for gamma rays. We want to repeat our model for the Milky Way for the universe, just to seek if Milky Way-like galaxies are the best place, the best galaxies to find life forms. Okay, and that's it.
A lot of, many questions. There are